Jai Hind everyone, myself Ankita, Faculty of Department of IT, AKGEC. Today I am going to discuss Unit 3 Software Design of the course Software Engineering BCS 601. In this video lecture, I will discuss about the basic concept of software design, architectural design, low-level design, modularization, coupling and cohesion measures, design strategies, function-oriented design, object-oriented design, top-down and bottom-up design. So these are the various design strategies that we are going to discuss today. Now, what is software design? So in the last video lectures, we have discussed about the software development life cycle. In the software development life cycle means how the software defines the period. The software development life cycle defines the period from the concept of the notion of software arises till the software is existing. So that whole life cycle of a software is known as software development life cycle. The first phase of SDLC was your requirement analysis and specification, where we were gathering the requirements, and after gathering of requirements, we were writing those requirements in a SRS form. We were documenting those requirements. So in your SRS, we were just focusing what are my requirements. We were not focusing how we are going to realize those requirements. So in the first phase of your SDLC, that is requirement specification and design, requirement specification analysis, we are only focusing on what of the requirements, whereas in software design we are focusing in on how. So once we have documented all the requirements in an SRS, we have to now find out how we are going to realize that document into our software. For that, we start with your software design. So software design will tell you how of a system. At the end of your software design, we will have a document which is known as software design document. So in requirement specification was your description of the problem, whereas software design is the solution to the problem. So when we have identified the problem, we have documented that problem, now we have to solve that problem. To solve the problem, we are doing the design. So software design is a process of planning and defining how a software system will be built to meet a specific requirement. So we have a requirements and we have to find out how that requirement has been realized. Okay. So a good system design strategy is to organize the program module in such a way that it's easy to develop. Now here, please mind it that we are not developing a software, we are just planning how a software will be made. And the good design will result better development. Now, objective of designs is first, it should be correct and complete. Whatever requirement that we have gathered, all those requirements should be included in the design. It should be correct. It should be understandable and efficient, because at the end, after this stage, we have the implementation phase where software developers will use this design to code. So it should be easily understood by them. And it should be efficient as well as maintainable. As you know, the nature of software is to change. The requirements always change. So our design should be able to handle those changes and include those changes. So whenever we start a design, there are two phases. One is your architectural design or a high-level design, and another one is your low-level design. In architectural design, we define the overall structure of the software system. So we are just making the blueprint of the system, where we are identifying what are the modules that will be present in my system and how these modules are going to interact with each other. So mind you, we are just focusing on the modules. We are not focusing how those modules will be realized. So it is the first step, that is high level design or architectural design, where we first try to identify the overall structure of the software. We try to find out the architecture of the software. We identify various modules, and then we identify how these modules are going to interact with each other. So it ensures that the system meets the functional as well as non-functional requirement. Now, functional requirement means the requirement that has been related to functional, whereas non-functional requirement means the requirement like efficiency, reliability, security. So we have to keep in mind that all these requirements are being, followed while designing the software. Also, we decide the technology stack and system platform. So, on which technology that we are going to, develop the software, either in Java or Python or anything else. So, all these stacks we are able to identify at your design phase, architectural design. At the end of this phase, we have a high-level design document which will have some architectural designs, which will tell what are these modules, what are my, how these modules are interacting with each other, what will be the technology stack I will be going to use, and all. So, these are your architectural design or high-level design. In your low-level design, what we do, we try to find out how the modules, we have identified the modules in your high level design. Now, how those modules will be realized, that is decided in your low level design. So, it describes how the individual components will be implemented. So, that is your low level design. Now, the purpose of low level design is to guide developers in the actual coding. So, how that component will be implemented. So, that is done in your low level design. So, we identify what are the various methods, functions, classes, relationships, all we are going to understand in your low level design. So, we have identified the modules in the high level design. Now, what data will be kept in these modules is identified in your low level designs. We also identify which algorithms or data structure that we are going to use. We also finalize the database tables. We also finalize data structures, algorithms, and logic flows. It will help to developers to write the code. Obviously, when we know the function, method and the classes, we know the algorithms, we know the data structure, we know the database table, it will be easier for the developer to write the actual source code. Also, how will be the error handled? All these will be kept in your low level design. At the end of low level design, we will have a low level design document. So, at the end of your architectural design, we have a high level design document, as well as in low level design, we will have the low level design document. Now, combining these two documents will have the software design documents. Okay. Now, next topic is your modularity. So, we have told in architectural design that we require modules to be identified. Now, how we are going to decide what modules we should form? So, before doing that, we should know the concept of modularity. So, first, what is a modular system? A modular system consists of well-defined manageable units with well-defined interfaces among the units. So, it consists of a manageable units which have some interfaces with other units. So, in the part of the properties of modular system, how we can identify a modular system? The first is that a module is a well-defined subsystem which potentially useful to other applications. So, when we are forming a module, we should be able to convince ourselves that that module will be used by other modules as well. We cannot make a module which is not used by anybody, right? That's simple. Next is a module should have a well-defined purpose. It should have a common functionality. We cannot club many different functionality into a common module and say this is a mixture module. No, that is not required. So, each module should have one single purpose. It should be separately compiled and stored in a library. It can use other modules because it is interfacing with other modules. It can use other modules. It should be easier to build and should be simpler from outside and then from inside. So, it's very important. So, whenever we are building the module, we are making the interface of that module, we have to make sure that the interface of that module is easy to use. So, if we are making very complicated module interface, nobody will be going to use that. So, therefore, module should be simpler from outside. Inside it can be complex, but from outside it should be simple. Now, when we talk about modularity, it says that a single attribute of a software that allows the program to be intellectually manageable. So, from the beginning of this course, we have been telling that the requirements change, and when the requirements change, our system or our process should be able to, include those changes as and when required. So modularity is a single attribute which helps to do the maintainability, right? So it enhances design clarity, which in turn eases implementation, debugging, testing, documenting, and maintenance of the software product. Now, as you can see from this diagram, we can see if we are, there is a just this limit, this is the area of modularity where we have the minimum cost, okay, and also the cost to integrate is also less. So you can see this very intricate balance between the number of modules. When we have less number of modules, the cost of integration is low, but total software cost is high. Whereas if I am increasing the number of modules, my cost to integrate is high. So we have to maintain an intricate balance to find out the number of modules. We cannot increase the number of modules into many modules. That is also not accepted, or we should not have very less modules. So we should have a balance of modules. And how we are going to decide that modules, that is our main issue. So for to understand that, there is two concept of coupling and cohesion. Now what is coupling? Coupling is a measure of interdependence between the modules. So if I have my modules identified in my system, how these two modules are interconnecting or communicating with each other, how they are dependent on each other. So that is your coupling. So two modules with high coupling are strongly interconnected, thus dependent on each other, whereas two modules with low coupling are not dependent on one another. So you can say you can depict the picture. Now this picture shows that it is the uncoupled environment where the modules are not at all interacting with each other. So if one module fails, no much impact will happen. But this is not physically possible, technically possible nahi hai. Next is loosely coupled. The modules are relatively independent. For example, you can see, so there is independence, but there is very less independence. So if one module fails, it will be impacted only these two. Now, if I have highly coupled coupling, so if only one module will get failed, all these modules won't be able to function. So you will be able to understand that what we require is loose coupling and not tight coupling. So if we have high coupling or tight coupling, our system will be not manageable. Now, coupling is measured by the number of interconnection between the modules, how the modules are interacting with each other. For example, how we say coupling? Coupling increases as the number of calls between modules increases or the amount of shared data increases. So if I have two modules, and in this module I have function A1, and in this module we have function A, 1, 2, 3, A, B, C. Now, if every of these three functions are calling all of these three functions from the other modules, so what? The number of calls to the other module function has increased. So it means the coupling has increased. So there is one point where the coupling increases. Next is the shared data. Suppose I have data A which is used by these two modules. So here also these two modules are coupled because they are using common shared data. If this module has changed the data to suppose 5 and it has changed to 6, so the impact will also happen in these modules. So that is the example of coupling. Designable high coupling will have more errors, obviously. Suppose this module 1 and 2 is using a data 5. Okay. Now if 2 malfunctions and change the data to 6, so if they are coupled, this one will also fail because it will have the corrupt data. So we can say high coupling will have more errors and low coupling will minimize the interdependence among the modules. So what is required for a good design? It is low coupling. So the interface should be carefully specified in order to keep low value of the coupling. Now example of coupling, we can say, suppose we have two modules. One is edit student record and another one is retrieve student record. So if I want to retrieve a student record, what I am doing, I am passing student name, ID, address and course to the edit student record, and then edit student record will in turn give me student record. Okay. Now why this is high coupling? Because I am unnecessarily passing all these 4 items. If I have to retrieve the data from the data store or retrieve student record. What is unique? Unique is a student ID. I can use only student ID to retrieve the data. Why is there a necessity for me to, pass all these data to it? So, this is the example of tight coupling or poor design, whereas this is example of good design or loose coupling. Now, the various types of coupling are data coupling, stamp coupling, control, external, common and content coupling. Now, you can see that data coupling is the best type of coupling, whereas the worst type of coupling is your content coupling, and it keeps on increasing like this. So, we are going to discuss all of these types of coupling in the next slides. Now, the first is your data coupling. So, before explaining any type of coupling, we have to understand that consider a scenario that we have two procedures A and B, and we can identify the number of ways in which they can be coupled. So, we have two procedures or two modules A and B, and we have to identify how they are coupled with each other through these various types of coupling. Now, data coupling says the dependency between module A and B is said to be data coupled if the dependency is based on the fact that they are communicating only to the passing of data. So, if we are passing only relevant data between two modules, we call them as data coupling. So, if we are passing the tramp data, it is not data coupling. For example, in this scenario, here we need to access the student record, so we have to pass the student ID. So, these two modules here is connected through data coupling. So, whatever data is required, we are only, sending that data. So, that is your data coupling. A good strategy is that no two module communicate through tramp data. So, here we were passing tramp data. Now, this is not example of your data coupling because we are passing the extra data, that's unnecessary data we are passing. Next is this is the best type of coupling that we want from our design. Next is your stamp coupling. It occurs when we are passing complete data structure from one module to the other. So, this entire data structure is never required. We only require some fields. So, we only need to pass some fields. So, for example, here we had passed the entire data set to the fetch the record of the student, which is not required. So, this is type of your stamp coupling. Next is your control coupling. So, if I have two modules and they are passing control information to each other. For example, if I have module A and I have module B. Now, if module B say if flag is equal to 0, do A, else B. Now, if this flag is set by this module, if this flag is, suppose flag is equal to 1, if this flag set by this module, we can say that A and B modules are control coupled because they are communicating through a common variable called as flag, which is set by one module and being used by another module. External coupling says dependency of module on another system which is external to the system. Suppose I have these two modules A and B, they are connected with the third external module C. So, this module is common to these two, right? So, we can see that this A and B are externally coupled because they are commonly using a common external software or you can say module. Common coupling says if A and B modules share the common data. So, if these two modules are sharing a variable, global variable, you can say C or D. So, this global variable is being shared by these two modules. So, we can say it is common coupling, right? External coupling says we are external tools or devices we are using, and whereas common coupling will say share data. Next is the content coupling. Now, it says when a module A changes data to module B or when the control is passed from one module to the middle of the another module, we call it as content coupling. So, suppose we have module B and we have go to temp. Now, this is a temp module. So, what are they doing? This is temp content. So, after this, right, after the completion of these steps, we are going to this module. And how we are going to come back, it is not certain. So, that is called as content coupling. Now, this is the worst type of coupling that we want. So, we can say The best type of coupling is data coupling, where we are only transferring or communicating only required data. And the worst type is content coupling, where we are just transferring the whole control of the module to some other module. That is your content coupling. Common coupling will say when you are using common variables, global variables. External coupling when you are using same common modules which is not part of yours. Control coupling when you are passing the control information. Stamp coupling says when you are passing the entire data structure. So these was your types of coupling. Next is cohesion. Now cohesion says, now I have my modules, I have some elements in my modules, how these modules elements are related to each other. So according to a design strategy, we should have high cohesion. So all those elements which are present in one module should be functionally related to each other. So we have to maximize the interaction within a modules. Hence, important design objective is to maximize the module cohesion and minimize the module coupling. Now, like your cohesion, we types of coupling, we have types of cohesion like functional cohesion. This is the best type of cohesion. Sequential, communicational, procedural, temporal, logical and coincidental. The best type is your functional cohesion and the first type is your coincidental cohesion. Now, what is functional cohesion? So, if I have a procedure, or we can say if I have a module having two operations A and B, now if both A and B are part of a single functional task, we call it as functional cohesion. Now, this is very good reason for them to be contained in the same procedure. So, suppose example, I am printing the result of the students. Now, in that I have two operations. First is retrieve the result, second is compute the result. Now, since these two are the part of the same module that is prepare the result, so this is a type of your functional cohesion. Next is your sequential cohesion. It says that A outputs some data which forms the input to B. So, I have two modules. I have one module in which I have two operations and A is emitting a data which B is consuming, and therefore they are kept into one module. We call it as sequential cohesion. Communicational cohesion says if X and Y both operate on the same input data and contribute toward the same output data, we are putting them in a same module. I have a module and I have two operations and both of them are having same input and they are both writing to the same output. Therefore, I have kept them together into one module. We call it as communicational cohesion, but it is not required. It is not expected. Why? Because since both of them have different functionality, they are just writing on the same, working on the same input and writing on the same output. Doesn't mean that we need to keep them in the same module. Procedural cohesion says if X and Y are both structured in the same way. Now, this is a poor reason for them to the same procedure. So, if X and Y both are structured in the same way, we are putting them into one module, then it is called as procedural cohesion. For example, if a particular student record, calculate the cumulative GPA and print cumulative GPA in case of procedural cohesion. Temporal cohesion means if X and Y perform at the same time and therefore we are putting them into same module. So, module exhibit temporal cohesion that is not good as functions are related by the fact that all tasks must be executed in the same time frame. Okay. So, if we are having some task that is being executed at the same time and therefore we have put them into same module, it is also not expected. Next is the logical cohesion. If X and Y perform logically similar operations, therefore we are putting them into a same module. That is also not satisfactory answer for putting the operation into one module, because it considerable duplication can exist in the logical strength level. Next is your coincidental cohesion. So, X and Y have no relationship with each other, but just by mistake or by accident, or you can say I have many different functionalities and I'm not finding out any specific module to them. So, therefore, I club them together into one module. No, this is not required. We don't want that. So, instead of creating two components, each of one part only, one component is made up with two unrelated parts. So, that is known as your coincidental cohesion. Now, coincidental cohesion is the worst type of cohesion that we want. So, we don't want unrelated things to be clubbed together into one module. And the best type is your functional cohesion. So, if they are functionally related with each other, we call it as functional cohesion. So, best type is your functional cohesion and the worst type is your coincidental cohesion. Next is your strategy of design. So first we have decided the modules, what are the going my modules. Now we have understood the notion of modules, what the module should be and how the module should be constructed. Now how we are going to identify those modules. Now there are two strategies for identifying those modules. First is your top-up design, top-down design. Second is your bottom-up design and third is your hybrid design. So a strategy of design is to organize the program modules in such a way that they are easy to develop and later to change. So if I am able to find my modules in such a way that they are easy to develop and also maintainable. So what is bottom-up designs? A common approach is to identify modules that are required by many programs. So in bottom-up design, what we do, we first identify the modules at the bottom. So how we are going to identify those modules? We have to keep in mind, we have to identify those modules first which can be used by multiple modules at multiple programs at the upper side. So first, so in bottom-up designs, we identify modules that are required by many programs. These may be file manipulation functions like maintain student detail, maintain subject details. Likewise, we can identify the modules. So we decide how to combine modules to produce the required logic, which is best done by writing several bottom modules. So first we identify bottom modules. We, understand the logic of these modules and then we club them together according to the requirement. Next is your top-down design. Here what we do, we start identifying the modules from the top. So first we identify the major module and then how to realize this major module? We'll divide into 3 sub-modules and further these sub-modules realized by 3 other modules. So here we are doing stepwise refinement starting from the abstract design. Now this is my abstract design and then each step the design is refined to a more concrete level until reach a level where there is no more refinement is needed. So we will continue doing this till we get the lowest level. Now what are the advantages of bottom-up design over top-up design and what is the disadvantage of top-down design? Now the advantage of bottom-up design is that here we ensure reusability. Why? Because when we are identifying the modules at the lower level, we are just keeping in mind that we have to identify only those modules which can be used by multiple other systems. So therefore here the reusability concept is more. Whereas in your top-down design, the modules can become specialized. Why? Because we are moving from top to bottom. Next is your hybrid design. What we do, we can say it is a sandwich approach where first we start from the abstract design and also from the bottom up. So pure bottom up or pure top down approaches are not practical. For bottom up approach to be effective, we must have good notion of top which design should be heading. So we should have some intuition about the modules, then only we can do the bottom up design. So therefore what we have done, we have combined the approaches of top down and bottom up and we call it as hybrid design. So for top down approach to be effective, some bottom up approach is essential for the following reasons. So we start with the top down approach and then in between we go for the bottom up approach also. So it will help to permit common submodules and the near to the bottom of hierarchy where the intuition is simpler. We start doing when we're able to identify, yes, these modules can be reused, so we start the bottom up, otherwise we go through the top down. Next approach of design is your function oriented design and object oriented design. Now as you have known that we have 2 strategies of programming. The one is your procedural programming and other one is your object oriented programming. So now these 2 programming approach is an example of you can say, a result of two type of design, that is functional oriented design, and the other one is your object oriented design. Now, function oriented design is an approach to software design where design is decomposed into a set of interacting units where each unit has a clearly defined function. So, we have a function, and these functions are, we have to identify the function depending upon the functionality. So, functional oriented design is a result of focusing attention to the function or procedure that focuses on a particular task. So, here we are, focusing on the task, and corresponding to the task, we are identifying the function. So, it uses the top-down approach where we start with a high-level description of the program does, and then we go down. So, refinement is done until we reach the statement level of a programming language. So, that is your function-oriented design. In this, we use structure charts, pseudocodes, flow charts, DFDs. All these are formed as a part of your function-oriented design, which can be represented graphically as well as mathematically. Another approach is your object-oriented design, where we are focusing our attention towards the data, towards the object. So, rather than functionality, we are not focusing on functionality, we are focusing on the objects. What functionality that object is doing and what data that object is possessing, it is all being measured. Now, object-oriented design focuses on real world things that are part of the problem to be solved. So, I have a problem. First, I will identify what are the objects, what are the things, what are the entities that are present in my system, and what entities, what data my entities is possessing, and how my object is, behaving. Now, therefore, in an object-oriented design, it is not dependent on any specific implementation, rather than it is dependent on the objects, which will have a behavior, that what things that they are going to do, and a state which changes when they do things. So, these are the behavior. Now, objects have behavior as well as state. Now, with respect of object, we also have the features of polymorphism, encapsulation, and data hiding, abstraction. So, this all forms a part of your object-oriented design. In object-oriented design, we are following a bottom-up approach, where we are first identifying those modules which are being used by multiple other systems. Now, in your object-oriented design, we are making class diagrams, interaction diagrams, state chart diagrams, and activity diagrams. So, all these diagrams we are used to designing the system, and it forms a type of object-oriented design. So, in this video lecture, we have discussed about various types of design strategies. Now, before that, we have discussed what is exactly design is, and what is the need of design, what are the advantages of design, and at the end of design, we have a software design document, and then we discussed about the various approaches of design, that is your top-down design, bottom-up design, as well as types of design, that is function-oriented design as well as object-oriented design. We also discussed in detail about the modularity, which tell us about the various coupling and cohesion measures. So, thank you for this today's lecture.